Hello everyone. In this video, we are going to study gamma ray microscope thought experiment. This experiment was first proposed by Heisenberg. It is usually called gamma ray microscope experiment. Suppose we want to locate the position, that is the x coordinate of an electron of an atom by means of microscope. The radius of the atom is of the order of 10 to the power minus 11 meter. Therefore, in order to determine the position of an electron with an uncertainty of about 10%, the radius of the atom, we must employ radiation of wavelength of the order of 10 to the power minus 10 meter, that is 0.01 Armstrong. It means that we must eliminate the electron with gamma rays of wavelength of order of 0.01 Armstrong. We have this figure over here. Here we have a rest electron, and when this rest electron is eliminated by gamma ray, the photons will scattered in these direction. So let us have a experimental diagram where we can observe each and every part clearly. Here we have a gamma ray microscope figure. Suppose, and in this figure we observe O, okay, and suppose initially the electron is at O as shown in the figure, is at rest, and to locate its position, suppose it is illuminated by a narrow beam of monochromatic light. Okay, this is the incoming photon, what we can say, monochromatic gamma rays proceeding in the x direction. Okay, let nu be the frequency and lambda be the wavelength of the incident gamma ray. Okay, then the momentum of an incident gamma ray photon in x direction will be h by lambda. Here we have P is equal to h by lambda, isn't it? Now, at least one photon should be scattered by the electron into the microscope. Okay, at least one should be scattered, and suppose we say this is the scattered one. Here we can observe this is the suppose scattered photon. Okay, in this process, the frequency and wavelength of the scattered photon is changed and the electron suffers a Compton recoil due to gain of momentum. At the instant when the electron is observed in the microscope, let twice theta be the angle subtended. See, here we have theta, this much is theta, and this is theta, and again this is theta. So the whole angle is twice of theta. Okay. So twice theta be the angle subtended at the electron by the diameter PQ of the instrument aperture. Okay. The scattered photon may enter the microscope along the surface of the cone whose semi-vertical angle is theta. Okay, suppose we considered here this photon is moving like this along the conical shape of this microscope. Suppose the photon enters the microscope along this OQ. Okay, and let nu dash be the frequency and lambda dash will be the wavelength of the scattered photon. Then the momentum of the scattered photon along OQ will be h by lambda dash. Okay. The image of the electron formed by the microscope will be an interference pattern which consists of central bright disk surrounded by alternate dark and bright fringes. Since the position of the electron may be anywhere within the central bright disk, the uncertainty in the position of the electron is the diameter of the central disk. Now, we'll go for the derivation. Here, you can observe del x is equal to lambda by 2 sine theta. Now, from where we got this equation? Okay. We all know from the Heisenberg uncertainty principle, del x into del px is greater than equal to h cross. So, by keeping this in mind, let del x be the diameter of the central disk. Then the uncertainty in the position will be del x. Now, according to the Rayleigh's criteria in optics, the resolving power of an optical instrument is the distance between the peak intensity and the first minimum of the diffraction pattern. And this expression is nothing but lambda by 2 sine theta. That is resolving power. Okay. So, in this case, we'll be having this resolving power as del x is equal to lambda by 2 sine theta. This is the expression for uncertainty in the position. Now, let P be the gain of momentum by the electron in the direction of recoil theta, where theta is a half angle subtended by the objective at the object, that is the electron. And lambda dash is the wavelength of the scattered photon. Now we can see that as we have seen along with the figure, the momentum of the incident photon P is equal to h by lambda. The momentum of the scattered photon, that is P dash, is equal to h by lambda dash. If the photon is scattered along OQ, then momentum of the scattered photon along x-axis is h by lambda dash into sine theta. And momentum imparted to the electron along x-axis is h by lambda minus h by lambda dash into sine theta. If the photon is scattered along OP, okay, in the another direction, then the momentum of the scattered photon along x-axis is minus h by lambda dash sine theta. Momentum imparted to the electron along x-axis is h by lambda minus h by lambda dash sine theta, which is nothing but h by lambda plus h by lambda dash sine theta. Thus, an electron can have momentum h by lambda plus h by lambda dash sine theta and h by lambda minus h by lambda dash sine theta. Since the term h by lambda in this equation is accurately known, and since the scattered photon can enter the microscope along any other direction making angle less than theta with the axis of the microscope, the second term represents the uncertainty in momentum. Let del px be the uncertainty in momentum. So, del px can be written as del px is equal to h by lambda dash into sine theta. So, by having this equation or multiplying this equation, we can have lambda x into, del x into del px is nothing but h or h cross. How did we get this? Because del px is 2h by lambda dash sine theta, and from the two equations, by substituting the value of del x and del px, we have h lambda by 2 sine theta into 2h by lambda dash sine theta. That comes out to be h, and the final equation we get del x into del px is equal to h. Okay, since in this equation the value of del px is minimum, this equation is consistent with the uncertainty relation, and that relation is del x into del px is greater than equal to h cross.